Welcome back to Z Physics, and welcome back to a new series in which we do a lot of past paper questions and we provide the links to these questions in the description. By far the best way to tackle this video would be to first off hit the like button, and straight after that check out the description of the video in which you'll be able to find some links to some questions and tackle these questions independently first of all, and then only afterwards check your solutions with this video. Just a little note that these are not official solutions, and please have a look at the OCR website for the official mark schemes. Okay, well, let's get started with question 4 from 2010. All of these questions, by the way, are applicable to all exam boards as the topics are very similar. Okay, so figure 4.1 shows a mass of a suspended mass which has been suspended from a spring. The mass is in equilibrium. By referring to the forces acting on the mass, explain what is meant by equilibrium. Well, there are two forces which are acting on this. One of them is the weight. Let's draw this a little bit better. I'm going to try and draw this straight down, and this here will be the weight, which is just mg, and there will also be a force from the spring which will be of the same magnitude but upwards. So we can say that an equilibrium would mean that the resultant force of the weight and the force from the spring is 0. Okay, on to the next one. The mass in A is pulled down a vertical distance of 12 millimeters from its equilibrium position. It is then released and it oscillates with simple harmonic motion. Explain what is meant by simple harmonic motion. So this is a classic question. And we can say that in simple harmonic motion, acceleration is proportional to the displacement. So it's proportional to displacement, and as well it is always, it meaning the acceleration, directed towards the equilibrium. Okay, next one. The displacement x in millimeters at a time t after release is given by x equals to 12 cos 7.85 t. Use this equation to show that the frequency of the oscillation is 1.25 Hertz. Now I'm going to go through this in quite a bit of detail just to explain this, so that will just help you guys revise this this topic. But one of the equations for simple harmonic motion for the displacement is that x is equal to a cosine omega t. You don't have to write this in quite as much detail when you're actually writing the exam paper, but my purpose of this video is to actually help you guys revise. So I'm going to go for this in quite a lot of detail. So we know that our amplitude, for instance, is going to be 12, and we know that omega, our angular frequency, will be 7.85. Now we know that omega is 2 pi f. So this means that 7.85 will be equal to 2 pi f, meaning that our frequency will be 7.85 over 2 pi, which is just about 1.25 Hertz. Okay, part 3, calculate the maximum speed of the mass. Now, in your formula booklet, you're going to find the equation for the speed of a harmonic oscillator, and that is that V is equal to omega, the square root of a squared, take away x squared. Now, x is equal to 0 at the maximum speed, so I can just say at V max. Therefore, the maximum speed will be given by omega A. Okay, so here is my graph. Now, a couple of things to notice. First of all, that the velocity time graph is the gradient of the displacement against time graph at any point. Now, initially the gradient is negative, therefore we're going to start with a negative velocity. The time period, and this will be one of the available marks, is going to be 0.8 seconds. That will remain unchanged because the time period of the graph above is 0.8 seconds. The maximum speed will be labeled as 0.942 meters per second. That is the peak speed really that we calculated up here. Okay, and the general shape of this graph will be essentially like a negative sign. You can also think about this in terms of calculus and derivatives. If you're doing A-level maths, this graph here is a cosine graph, and the derivative of cosine is negative sine. Okay, folks, on to the next one. Okay, next one, which is question 3 from June 2010. State 2 conditions concerning the acceleration of an oscillating object that must apply for simple harmonic motion. This question appears again and again and again. It's really, really important. That's why we're solving it so many times. So remember, number 1 would be that acceleration is proportional to displacement. And remember, acceleration is also always directed towards the equilibrium position. So it is always directed towards the equilibrium position. Okay, part B, figure 3.1 shows how the potential energy in millijoules of a simple harmonic oscillator varies with displacement. Okay, this is a typical potential energy curve over here. So on figure 3.1, sketch graphs to show the variation of the kinetic energy of the oscillator with displacement. Label this graph K. Okay, so I'm not going to forget to label this. I'm just going to underline that. And the rule that we're going to be using here is that whenever the potential energy is 0, then the kinetic energy will be a max, which is 18. There's 18 millijoules in the system, and vice versa. So when the potential energy is at maximum, the kinetic energy is going to be 0 at those 2 points. So essentially at the maximum displacement we have 0 kinetic energy, and it will be in a way a mirror curve. Let's see if I can draw this on my digital whiteboard like this. I can be a little bit more careful than me in the real exam, but yeah, so this curve here is K. This is the kinetic energy. Now the total energy of the oscillator is just a horizontal curve because the total energy that is always constant, and that's just going to be 18 millijoules, which is just a straight line. Please use a ruler in the real exam. Remember, I don't actually have a ruler on my digital whiteboard, but this here will do. And let's label this T. Okay, so this here is K and that is T. Okay, next one, use the figure to determine the amplitude of the oscillations. Well, the amplitude is just the maximum displacement, which is plus or minus 0.04 meters. Just checking the units, yeah, no problem here. So we can just write this down, 0.04 meters. Okay, next one, we're looking for the maximum speed of the oscillator of mass 0.12 kg. Now, because they've given us the mass, we could really easily just use the kinetic energy, because we know that the maximum kinetic energy is to be found here. So that's 18 millijoules. So I can just say that K max is 18 times 10 to the power minus 3 joules, so I can just set that equal to a half mv squared, and this is exactly what we're going to do. So what we're going to write is 18. I'm going to write this as 0.018 is equal to a half times the mass, which is 0.12 times v squared, which means that the maximum speed, let's call it Vmax, will be equal to the square root of 2 times 0.018. I'm going to divide that by the mass, and the mass is just 0.12. Plugging that into a calculator, we're going to get about 0.55 meters per second. Okay, the frequency of the oscillations, well, this here can be simply be found just by remembering the fact that if we have our maximum speed is always just plus or minus omega a, which is 2 pi f multiplied by a. So we know what our amplitude is, just 0.04. Just here we know what our maximum speed is, so all we need to do is just rearrange for the frequency and plug in some numbers. So the frequency will be equal to Vmax divided by 2 pi a. Our maximum speed is 0.55 divided by 2 pi times 0.04, and that's going to give us about 2.2 Hertz. Okay, next one, which is about resonance. Resonance can either be useful or a problem. Describe one example where resonance has a useful application and one in which it is a problem. For each example, identify what is oscillating and what causes these oscillations. Okay, and here's my answer. So for a useful application, I've chosen microwaves. There are many different ones that you can choose. Have a look at the mark scheme for some more ideas. EM radiation from a microwave oven, for instance, will cause water molecules to resonate. When this is actually happening, the driving frequency of the EM waves matches the natural frequency, causing maximum amplitude. This is not actually part of the mark scheme, however, in more recent questions seems to be appearing very, very often. So this statement here that the driving frequency matches the natural frequency, I've decided to include in both of those answers. For the second example, for a problem, wind can cause bridges to resonate and hence cause damage. Okay, on to the next question. Okay, next question, which is question 2 from a 2011 paper. So figure 2.1 shows a mass attached to the end of a spring. The mass is pulled down and then released. The mass performs vertical simple harmonic motion. So part A or part I, define simple harmonic motion. So once again, a really typical question. Acceleration is proportional to the displacement, and remember, acceleration is always directed towards the equilibrium. Okay, the next one, mark the following statements about the oscillating mass spring system as true or false. The period of oscillation is constant. Well, that is true. So in simple harmonic motion, the period of oscillation is independent of the amplitude. So even if it's losing some energy, it will be remaining constant. The net force on the mass is equal to its weight. Now that is not the case if it's in equilibrium. For instance, it will be equal to 0. If it's not in equilibrium, it will be equal to some values in between, but it will not be equal to the weight. The acceleration of the mass at maximum is a maximum at the midpoint of the oscillations. Now the midpoint of the oscillations is the equilibrium, so at that point the acceleration will be a minimum. So this here is also false. And finally, the velocity of the mass is proportional to the displacement. That's incorrect. It is indeed false. In fact, the velocity of the mass is maximum when the displacement is 0. Okay, next one we have an extended writing question, which is a 5 marker. A student wishes to investigate whether the period of the oscillation of a simple pendulum is constant for all angles of swing. Describe how the student should carry out the investigation. Sketch the apparatus. Details of how the measurement would be made. How these would be used to form a conclusion. The major difficulty likely to be encountered, and how we could overcome this. Okay, so let's have a look at my answer. Okay, so here are my answers. First off, we have a label diagram. It's a relatively simple one. We have just a simple sketch with our pendulum, which is pinned against a protractor, and we can actually measure using the protractor the angle. I've also included a little artistic diagram of a stopwatch. Now on to our measurements. First off, we're going to be varying the angle and measuring the time period. I always find it useful just in any experiment to say, what am I going to be varying? What am I going to be measuring? We're going to be measuring the time period with a stop clock and the angle with a protractor. There's going to be one major difficulty in our measurements, and that is that the angle is going to be decreasing rapidly during timing. In other words, as soon as I release the pendulum, the angle will want to decrease very, very quickly. And a solution for that would be to time half an oscillation with a video camera or an on-screen timer. The typical solution sometimes for a different system, something like a spring, might be to time 10 oscillations, but in this case that will not work, because after 10 oscillations the angle will be significantly different than our initial angle. So just use a video camera on a phone with an on-screen timer. How are we going to form a conclusion? Well, we're simply going to plot a graph of the time period against the angle, and we're going to use that to form our conclusion. Okay guys, next one is question 4 from a paper from 2013. Figure 4.1 shows slotted masses suspended from a spring. The spring is attached to fixed support at its upper end. So when the mass are pulled down a short distance from the equilibrium position, then they release, they oscillate. We have the frequency is F and the mass is M of the masses. So two students make two different predictions about the relationship between F and M. One of them says that F is proportional to 1 over M. The other one thinks that F is proportional to 1 over root M. Describe how you test experimentally which prediction is correct, including your answer, the measurements you would take, how you would use those measurements, and also ways of making your test as reliable as possible. So let's have a look at my measurements first off. We're going to measure the mass M with a top band balance, and we're also going to be measuring the time period with a stop clock. I'm going to calculate the frequency using 1 over the time period. The only way to decide really would be to plot the graphs of F against 1 over M and F against 1 over root M. The correct relationship will produce a graph which is a straight line through the origin. So far I've described what measurements I'm going to take, I've described how I would take these measurements, and I've also discussed how I would decide which prediction is correct. Now let's also answer how to make the test as reliable as possible. These time periods are notoriously tricky to actually measure, so what we're going to do is we're going to time 10 of those oscillations, then divide our answer by 10 to get one of the time periods, and that will ensure that we have a lower percentage uncertainty. Okay, on to part B. When the masses hanging on the spring are 400 grams in total, they oscillate with an amplitude of 36 millimeters and a period of 1.2 seconds. Calculate the maximum kinetic energy of the masses. So Anytime we want to calculate the maximum kinetic energy, that's just a half m times the maximum speed squared. Now, what is the maximum speed? Remember, the max speed is found by omega times the amplitude, so it's going to be 2 pi f times the amplitude, which will be 2 pi 1 over the time period, which is 1.2, multiplied by the amplitude, which is 36 times 10 to the power of minus 3. And if we put that into a calculator, we're going to get about 0.188 meters per second. Let's plug that into our kinetic energy formula. So it's going to be a half. Now the mass is 400, which is 0.4 kilograms, multiplied by Vmax squared, which is 0.188 squared. And let's plug that into a calculator again, giving us 7.1 times 10 to the power of minus 3 joules. Now, to calculate the maximum acceleration of the masses, we're going to use the equation for simple harmonic motion. And this is a really good question because you really need to understand what's actually happening in simple harmonic motion to answer this question correctly. So the maximum acceleration occurs at maximum amplitude. So I'm just going to make a little note over here. You don't have to do that in the exam, but just to help you guys really understand that the maximum acceleration occurs at maximum amplitude. So the equation for simple harmonic motion is a is equal to minus omega squared times x. So the maximum acceleration occurring at the maximum displacement, there's only one amplitude really, so I'm just going to remove the word max. So a will be minus 2 pi f squared multiplied by x, and we can just plug in some numbers. So it's going to be minus 4 pi squared, then it's f squared times the amplitude, if this here is a max. So this here will then be equal to minus 4 pi squared times the frequency, which is 1 over 1.2 squared, multiplied by the amplitude, which is 36 millimeters. So it's going to be 36 times 10 to the power of minus 3. And if we plug that into a calculator, we're going to get 0.99 meters per second squared. Okay, part C lists the different types of energy involved in the oscillations of this mass spring system. Describe the energy changes when the mass moves from the lowest point of the oscillation to the highest point. Okay, so first off, let's have a look at the kinetic energy. Well, that is 0 at the maximum amplitude, so it's going to be 0 at the highest point, or let's say, yeah, so let's just write at the highest point, and at the lowest point, at the lowest point, and it's also maximum at the equilibrium, because that's when the mass and the spring are moving the fastest. So maximum at the equilibrium. The next one is the gravitational potential energy, which is commonly written as GPE, and this is obviously a max at the maximum height and decreases as the mass goes down. Now the other force in our list is elastic potential energy. So elastic potential energy. And the elastic potential energy will be increasing as the mass is going from the equilibrium to the amplitude. Okay, on to the next one. Okay guys, another question from June 2013 from OCR. Once again, check the question in the link below. So we have an object which is oscillating with simple harmonic motion. Place a tick in the box against each true statement that applies to the acceleration of the object. The acceleration is in the opposite direction to the displacement. Yep, that is always true for simple harmonic motion. It's directly proportional to the amplitude squared. Nope, we're confusing this with intensity. Increases as the displacement decreases. Yep, so that's not correct. The opposite is true. Increases as the speed of the object decreases. Yep, that is true. For instance, something like a spring that is oscillating, the further away it is actually stretched, or even something like a pendulum. So let's use a pendulum as a more visual example. As the pendulum is actually oscillating and it's reaching the end of its trajectory, it's slowing down. So here it is slowing down, but it has the maximum acceleration. Okay, now that we have explained this, let's have a look at part B. The graph in figure 3.1 shows the variation of the velocity v of the object with time t. Okay, that's fine, and we have this nice sinusoidal graph. Check out the units. We have meters per second and seconds on the x-axis. Use the graph to determine the frequency of the motion. Well, the frequency can be found by the time period, and we can see that the time period will be 1.2 seconds. So the frequency will just be 1 over the time period, which is 1 over 1.2, which is about 0.83 hertz. Okay, now how can we figure out the amplitude of the motion? It's actually a really interesting one. So far we only have velocity, and the equation that actually links those two quantities is the Vmax equation. So it's actually a pretty tricky question. Now remember, Vmax is omega A. Now, where does this equation come from? The speed of harmonic oscillator is given by plus or minus omega, the square root of A squared minus X squared. And at maximum speed, V is equal to plus or minus omega, the square root of A squared minus 0 squared, because then we're just at the equilibrium. So the displacement X is 0. So V will be plus or minus omega A. Okay, well, we can determine our Vmax, which is going to be just here, like so, and that is 0.08 meters per second. Okay, well, let's do this. We already have the frequency, so I can just say that Vmax is equal to omega times the amplitude, which is equal to 2 pi f times the amplitude. So we know that Vmax is 0.08 meters per second, which is equal to 2 pi times the frequency, which is 0.83 times the amplitude. So we can directly rearrange for A. So A will be 0.08 divided by 2 pi times 0.83, and this is going to equal 0.015 meters, or about 15 millimeters. Now let's see whether we can calculate the maximum acceleration of the object. So the maximum acceleration will be occurring at the amplitude. So remember, simple harmonic motion, the defining equation for simple harmonic motion is that A is equal to minus omega squared times x. So at the maximum acceleration, we're going to have minus omega squared A. Okay, well, the maximum acceleration will be given by minus 2 pi f, and then the whole thing is squared times the amplitude. So this will be minus 2 pi times 0.083. Let's see if that was my frequency, or it was 0.83. So just always double check your numbers, guys. So 0.83, and we're going to square this. And we're going to multiply by the amplitude, which we've just found to be 0.015, giving us 0.42 meters per second squared. Okay, next one here is about resonance. With the help of a suitably labeled diagram, explain what is meant by the resonance of the mechanical system. So here is our graph. We have the amplitude on the y-axis, and we have the natural frequency, we have the frequency on the x-axis. Notice that I've labeled here the natural frequency, so the graph is tending towards a single peak. Resonance occurs when the driving frequency matches the natural frequency and the amplitude has reached the maximum. The amplitude of the oscillations would then be at a maximum. State and explain an everyday example of resonance. A microwave oven would be a perfect example. EM radiation will then be matching the natural frequency of the hydrogen molecules in the food, and thus resonance will occur. They get heated up. Okay guys, we're going to stop here for now. Well done for doing some practice on oscillations, and well done for revising. Thank you very much for watching, and I'll see you in the next video.